Hello everyone. So today we are going to take another example on STAAD Pro, and this time it will be a pedestrian steel bridge. And let us start by looking at our drawing for this bridge. So it will be a truss, and we have the option to choose the type of the truss. As I said before, the Pratt truss is the most economical type of truss because the diagonals in this case will be under tension force when I have gravity load, and most of the time most of our bridges will be under gravity load due to the high superimposed dead load value. So in this example we will have a bridge spanning between two concrete buildings. So if I look at this detail on the right, this detail is for the bottom chord connection with the concrete at the left side, or sorry, at the right side. So here, if we can see, we have an RC corbel and we have a base plate connection with this RC corbel, and here we have what we call a bearing plate, and sometimes the flange will be directly bolted with the base plate, so the holes will be within the bottom flange and the base plate. But in this case, the bearing plate is welded to both base plate and the bottom flange of the bottom chord, and I will tell you why in a few moments. Now, by looking at the other side, I'm providing a roller connection. What does it mean? I mean that this connection is a sliding connection in the x direction. If we consider this to be the x direction, so this connection allows the movement in the x direction. And how can I accomplish that? I use what I call sliding bearing detail. So I have a bearing plate here, and it will be welded to the bottom flange of the bottom chord, and below this bearing plate I can provide a thin stainless steel plate. It will be around 1 to 2 mm, or I can prepare the bottom surface of the bearing plate to be very smooth if I don't want to use the stainless steel plate. So the bottom surface of the bearing plate must be prepared and grinded to be smooth to allow this smooth sliding above the elastomeric pad without any friction, or to reduce the friction as much as possible. We have this elastomeric bearing pad, and there are many suppliers that can provide this elastomeric bearing pad, and sometimes it can be reinforced, and I can uh, provide the supplier of this pad with the required pressure. Simply I calculate the vertical load at this connection, and I have the bearing plate surface area, so I give him the required pressure under ultimate load combinations, and he will design this elastomeric pad, and sometimes he can provide some steel inserts, and also this elastomeric pad can also allow for slight rotation. Okay, so it depends on the supplier of these pads and the requirements I'm providing. In my case here, I only needed to resist vertical load, the compression load coming from my bridge, and below this pad I have the base plate, and at these sides, and we will see in plan in a more clear way, I have what I call steel stopper. Okay, and these stoppers will be welded to this base plate. Here I'm providing a PGP weld, or it can be CJP or even fillet welded to the base plate. So these stoppers are designed or are provided to stop the bearing plate from sliding outside of the base plate. So it's providing like uh, a guiding for this bearing plate. Below we have the grout and the reinforced concrete corbel. So this is a sliding detail in the X direction. So we can look at it in plan. This is the bearing plate, and here with the dotted uh, hatch, we have the elastomeric pad, and the steel stopper is all around here. So because I'm only allowing the movement in the X direction, I can see no gap between the stopper or the guide and the bearing plate. The bolts in this case are provided outside of my bearing plate, and it will be directly fixed to the reinforced concrete corbel. In other cases, sometimes I don't have this sliding detail, or it's provided in a different way. Sometimes I don't have the bearing plate, so, or even if I have the bearing plate, the bolts will be within the flange of the bottom cord and the bearing plate, and it will be also connected all through the base plate to the concrete. So in this case, the bolts will be within the bearing, and there will be no guides at the edges of the base plate. So the movement will be accomplished within the oversized hole of the bolts. If I want to make this more clear for you, let me just take this and show you another example for another type of uh, base connection that allows movement. So in this case, I will have, for example, this as the bearing plate, and as I said, I will have the anchor bolts within the bearing plate. So in this case, how can I allow the movement? So I will provide, let's see, at all 4 bolts, I will provide like a slotted hole, and this slotted hole will be in the bearing plate and the bottom flange of the beam. And I will have a standard hole inside the elastomeric pad and the base plate. So the sliding assembly will be the bearing with the stainless steel, if I use stainless steel, and the bottom flange, and all this assembly will be sliding above the elastomeric pad. So all these plates will have an oversized hole or a slotted hole, and it will allow the movement of this assembly above the elastomeric pad. So here the movement will be accomplished through the slotted hole. I'm drawing this slotted hole in a quick way. For sure it will have fillet or radius at the corners. And here when I have a free connection where the movement is allowed at both in both directions, in this case I will have, instead of the slotted hole, I will have what I call an oversized hole. And this oversized hole will be designed for the required movement in both directions. For sure, in this case, I will need a washer, but this washer will not be welded to the base plate. Okay, it will not be welded to the base plate or to the bottom flange of the bottom cord, because I want to allow the movement at this connection. So I just want to clarify that we have more than one type to accomplish this movement. For sure, why sometimes I need to provide the bolts within the bearing plate, because sometimes I might have tension at the support. It's it's not very common to have tension at these bridges, because most of the time the dead load is very high in comparison to any uplift load coming from wind. However, it can happen. Also, even if I want to use this plate and I have tension force at the support, it can be done also in a different way. In this case, let me show you in a quick sketch how to do that. For example, I will take a front view for the bottom cord. In this case, just to show you how it will be done. Now the bearing plate will be larger than the bottom flange in this case, and here we will have a stainless steel plate. So in this case the weld will be here. Okay, as I said, we also might have a stainless steel plate, and here we will have the elastomeric pad, and then the base plate with the bolts, or the bolts can be whatever, only in the base plate. Now the thing is with the guides or the stopper. So in this case, I can provide something like that for the stopper, and this gap will be only limited to few mm, 2 mm maybe for tolerance. So now these stoppers will provide like a guide for this bearing plate in this direction or in the other direction through this gap. However, any uplift force will be resisted through bearing surface. Here I will show it in green. So if I have like a tension at the uh, bottom chord, it will be transferred through bearing at both sides here. And this also can be done in the other direction. So in this way, I will have the bolts only at the base plate. However, through the stopper, I will resist any uplift, and I will ensure that the bottom chord will not come out of its place. So these stoppers will provide like stopping for any uplift force, and it will be resisted through bearing. For sure, I will then design this stopper for any uplift force here. So this is another way to do it. What I need to show you that we have different types and uh, many ways to design these sliding plates, and uh, it depends on your preference, on your calculation, on the application. If you are using this for bridge or for a flooring system, so we have different or many scenarios to do that. So, as I said, this is the guided connection in the x direction. Sometimes we have it in both directions, and I will say now why here we have like a free connection, so the movement is allowed at both direction, and here I'm having the movement allowed only at one direction. So just to clarify again, the movement here can happen right and left. Okay, this bearing plate can slide right and left. Here it can slide right and left, up and down. So the movement is allowed at both directions, and the stoppers we can show them here. On the right, here we have a pinned connection. It doesn't allow any movement in any direction. And here I have a guided connection in only the vertical or in the y direction. So if I look at the configuration of the supports of the bridge, okay, so the support will be through the bottom chord only. I have pinned where no translation, no movement is allowed in any direction. At the far end, I have a guided connection with the movement allowed in the x direction. Here I have the movement allowed in the y direction, and here I have the movement allowed in both direction. And this is a very common uh, type of supports for steel bridges. So why do I provide these sliding connections? Because when I'm connecting a steel bridge or a platform or any corridor, let's be more general, between two concrete buildings, I can expect movement at this floor at both buildings from the concrete. Okay, so if I have like wind load or seismic load at the concrete building, I can expect a drift value at this level, and it will increase as I go up. So if I don't provide this guided connection, if I provide pin connection at both ends, any movement from the concrete will be transferred as axial load in the steel bridge. So now I have the steel system and the concrete building, or the steel bridge and the concrete building are sharing forces. So now I have a rigid link between these two buildings. Any force, assume that this building is moving to the left and this building is moving to the right, different mode shapes. So this bottom chord will have a compression load. And in this case, I need to model both systems together to capture this integration of forces. And if I design this steel bridge separately, it will not be accurate at all. Okay, so that's why when I provide these expansion or movement at this support, I must design the distance here for drift or displacement from concrete at the left, or the building at the left, plus displacement from the concrete building at the right. Here I can, here is 2, okay, and also any displacement coming from the steel itself. And most of the time this will be due to temperature load, self-straining action. So the steel can provide some movement due to expansion or contraction. Okay, so I will add all these values. I will take the first two values from the designer of these concrete buildings at the specified level here, and the steel I will get it from my model. Now in the other direction, so this value also will be the same for both supports in the x direction. Now in the y direction, it will only come from my steel, okay? In this case, I will consider the steel movement, and it will be, as I said, due to temperature load most of the time in the y direction. So I'm calling it delta steel transverse, in the transverse direction, or y. Okay, and this will be the value for the movement here. Okay, it will be at both supports left and right. So basically, this is how I choose my supports for my steel bridge above any concrete, or spanning between any concrete buildings. For sure, if I have like steel columns instead of concrete buildings, like the bridges at the main roads, I have like steel column at the right, and sometimes stair if it's pedestrian bridge. So in this case, I don't need to worry about all these complications. I will design the full system, two columns or two truss columns at both sides with the bridge spanning between them. But I wanted to show you this because it can happen in many projects, especially if I'm designing like steel bridge linking two concrete buildings together. So in my example, I'm assuming a bridge span of 30 meter. Width of the bridge, this is a top view for the bridge, like a plan. 3 meter, and this is an elevation front view. So in this case, my bridge will have a height of 3 meter. I will assume that the bottom floor is accessible and the roof or the top level is only a cover. So it will not be an accessible roof. Okay, here is the load criteria for the bridge, and we will get to this later after we finalize the modeling of the bridge and we start to apply the loads. So now let's move to the STAAD again. So this time we will not model the bridge in the conventional way as we did for the steel warehouse. So we will not use these tables. We will use structure wizard. So we will click on it. And here we have prototype models. So these models are already provided in the database here for trusses, frames, services, etc. So we will stick with the truss models. And before that, we need to change the units once again from here. So we will go and select SI metric. Okay. And then we will choose our truss prototype. We will have a total length of 30 meter, a height of 3, a width of 3, and number of bays will be 10, with each bay of 3 meter length. And apply, and here we go. Here is our truss, and we will merge this with our STAAD model. Yes, and we will have the base point at 0, 0, 0, and we click OK. So now we have this bridge, 30 meter long, 3 meter wide, and 3 meter high. So now we will go and choose the Pratt truss. And as we said, the Pratt truss is an economical truss because the diagonals will be under tensile force and they will not be a compression member, generally under gravity load. So we don't have to worry about buckling. So we will go here and adjust our model. So these diagonals must be the other way, must be coming in the other direction. So I will delete simply, and I will mirror these on the left side by choosing the command mirror. I will choose the plane of mirror here. It will be YZ. So YZ and any node on the plane and copy. So here we have our Pratt truss with the diagonals as we can see them in the model. Okay, now let's move on. We have two floors. The upper floor will have light metallic cladding like purlins with sheeting. So in this case, the spacing between these members that will support the purlin is typically 3 meter, and the purlin can easily span 3 meter. So the main framing is okay for me. However, and we will go then to the specifications to assign the releases. as we are dealing with a truss, vertical truss, and in the other direction, these members are supporting the metal cladding, so I need to make them release because I don't need to introduce a moment connection at each joint here. It will be too much for me. And in this case, I will provide some kind of horizontal bracing. So basically, the lateral load will be transferred through the top and bottom chord because the glazing will be supported at top and bottom beam. It will not be directly supported at the vertical members. So after that, it will push the structure. We are tracking the load path here. And if we are having hinged joint here, I don't have any stability system that can resist this lateral force. So either to have a moment value, and in this case, I will transfer the load directly to the bottom service, and then I will deal with the bottom service in its turn, or I have to provide the horizontal bracing. So the force will be transferred through the horizontal bracing to the end base on the right and on the left where I do have supports with the concrete. So how to do that? I will provide bracing, and single diagonal bracing will be fine. I don't need to provide heavy bracing. Okay, now the load will be transferred along the top chord through the horizontal bracing to the end base here. Okay, so what about the bottom chord? The bottom chord, as we said, we have a concrete flooring. So this concrete flooring will be supported above secondary beams that will be transferring this load to the main girders. Okay, so how to do that? I can have a spacing of 3 meters, but first I need to check the metal plate, the steel plate, corrugated steel plate, if it can span the 3 meter. Now, most of these corrugated steel plates can easily span from 1.5 up to 2 meter, sometimes 2.5. Now for 3 meter, I might face some problems, especially if I have high load. So let us go to the catalog here that I'm choosing, Canon, and I'm choosing this P3623 model. This is the dimensions of the corrugated steel sheet. I have the ribs here, and I have the thickness within the ribs, and then I have the topping to get the total thickness of the concrete. So here I chose, depending on the thickness of my slab, 125, and it will have a 0.76 thick steel deck. And now for the maximum unshored span, you can see that I have around 2 to 2.12 meter. So for this thickness, I can't go more than 2.12. Now, if I'm using 1.21 millimeter steel deck, I can go up to 3.265. However, it's very preferable to limit my span to 2.5 generally. So in this case, I will need to provide an additional beam at this span. So instead of 3 meter, I will provide an additional member here. So my span will be 1.5. So how to do that? Simply, I can do it in multiple ways, but I will select my members here like that, and I will copy them in the x direction for a distance equals to 1.5 meter. And here I have 1.5 meter for the span of the steel deck. So in this case, just to show you, now my steel deck will be spanning 1.5 meter. Okay, this is 1.5 meter. And then I will have the concrete topping above it. Okay, now I have my members. So I will once again track the load. So as I said, I will have a curtain wall, and it will be supported at top and bottom chord. And it's very important uh, to 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 see the fixation of the cladding on my structure, to check it with the supplier, because it will influence the loads application on my model. So here at the top, or the top chord will take half of the lateral load. After it will hit the cladding, it will be transferred half of it at the top chord and the other half on the bottom. So here at the bottom, it will hit the bottom chord, and I will have secondary release members. However, I have a diaphragm action. So in this case, I have two options: either to model the concrete slab or to provide like a bracing, and this bracing it can be used during construction or even before pouring the concrete slab, or even only to model the diaphragm action. So in this case, if I have any load hitting the bottom chord at any point, through this bracing, it will be transferred directly to the supports, similar to what I did on the top chord. But as I said, again, I will repeat, the bottom chord will have a concrete slab, and the concrete slab, it will act as a diaphragm naturally. Okay, so it will transfer the load directly to the end base here. For sure, I have sometimes I might have some concerns about the flexibility or the rigidity of this diaphragm, as we learned in the seismic session, that the limit between the flexible and the rigid diaphragm is the displacement of the slab at the middle, or the maximum displacement of the slab. So if I have a high displacement of the slab at the middle, especially if I have a high span or larger span, 30 meter, I might deal with it as semi-rigid diaphragm. So it will not transfer the full load to the supports. It will have some bending in the Z direction. So preferably, if I'm not designing any composite slab, so I'm using this concrete slab as a topping only, as a load to applied load on my floor, I can simply add these bracing, and these bracing will act with me structurally, and they will transfer the load from these points to the end base. Okay, now I can use the mirror command again. If I don't do this bracing, you can see that I will have a huge displacement at the bottom. And I can show you that after we finalize our model, that in case I remove this bracing, I will have a stability issue in my model. Okay, copy, and here we go. And now I modeled my truss, my bridge, and I provided the lateral stability system, which will be through the horizontal bracing that it will transfer the load to the end base. Okay. So now we will move to the properties. We will select some profiles and assign them to my model, to the model. And after that, after we finalize the design, we will recheck these profiles and adjust them as needed. So let us use hot rolled profile in this example. So I'll go to the section database and I'll go to the European profiles and I will choose the IPE and let us go with IPE 300, add, and now I will use the IPE 300 for top and bottom chords. Okay. After that, I can make two profiles for the top and for the bottom. But for now, I will just use one profile for both. And for the vertical and the diagonals, I will use a tubular section, square, hollow section, and I will start with, let's say, 120 by 10. Let us now assign beams parallel to X, assign to view, again display whole structure, and now select parallel to Y. I will assign the tubes, and for the diagonals, I can select them manually. Okay, and do the assignment again. For sure, I can expect higher loads at the diagonals near the support. And in this case, I can use different thicknesses. For example, I can go for 120 by 12, or in case it's very safe, I can decrease the thickness at the middle portion. However, for now, as I said, I did not do any design, so I will just propose any profiles and I will verify them later. Now for the secondary, at top and at bottom, I will use also one profile for now, and I will choose IPE 180, select beams parallel to Z, and assign. Okay, what is left here? I can select by missing properties, missing property. I have the diagonals, the horizontal bracing at top and bottom chord, and also I will choose now one profile for both. I will use pipe. I can use angle or double angle also. So let us use this time double angle. Okay, L70 by 70 by 5, and here the spacing, which is the spacing between the angles. So here I have one angle and the other one. It will be back to back. So this is the spacing, and generally it depends on the thickness of the plate in between. So I can typically use 6 mm, for example. So here it's an inch. I need to adjust the units from the start. Now 70 again by 5. Let's go to the angle, and here I will provide 6 mm. I will add. Okay, once again select by missing property, and I will assign. Okay, now let us see the model in a rendered view. Here we have our truss in a rendered view. It looks nice. Now the material, steel, and I will go to the specifications. Now for the specifications, I will assign the releases first, my, mz, add, and let us start by assigning the vertical and the diagonal members. And also the secondary and the bracing as well. I'll do them separately. Okay. Now we can use sometimes the truss, but for the truss, it does not calculate the own weight of the member itself, so it's preferable to stick with the release command. So now, as we assigned our releases, let us look again at the specifications and see if the releases are adequate or I need to adjust and maybe provide some fixity to some members. Now, let us track the load. I have the load is hitting the wall. Assume it's a wind load because I'm not assigning any seismic in this model. And it will transfer now through the diagonal at the roof to the end frames here. Okay, so and then it will be transferred to the support. However, this frame, as I'm providing also releases for this frame, so in this case it will be unstable because at the end, as we did in the typical steel warehouse, I provide at the end or at the sides, if I have to say, like a vertical bracing X bracing, or if I cannot provide an X bracing, I can provide alternatively a portal frame, a rigid frame with moment resisting connection. Okay, so in this case, to provide stability for this model, because I will transfer the load from the top level to the lower level. How can I do that? I need a stable frame at end so it can transfer the load properly to the support here. So in this case, it's very important to have a moment frame at these members. So I will toggle the specifications also at the end. And here for the top connection of the column also, for sure I need it to be moment because the joint will be rigid. Also I will toggle now. Now the bottom, it's okay. I can keep it hinged like I have a frame with a hinged base. So it's okay. I don't need to adjust it to provide stability. So I will have now a stable model, and it's very important to track the load path and to understand the stability system of my model. Otherwise, I might face a big problem. And as I said before, the stability is a very important issue, and it's critical for my safety, for the safety of the structure. Okay, so now let's go to the supports, and I will assign the supports, and I will follow the articulation I provided here in the drawing. So I will have a pinned support here, and I will have here a guided connection in the Z direction. So I will create and I will go to fixed butt. So in this case, I will allow MY, MX. I will release the moment, and I will release the Z. Okay, and now I will have this connection guided in the X direction. So I will do this again. I will release the moment and I will release it in the X direction. And the final support, it will be released in both X and Z direction. So here I have my articulation. This is pinned. This will allow the movement in the X. This will allow the movement in the X and in the Z, and this will also allow the movement in the Z. So now let's move to the load applications. So I will start to add the loads. Dead load. Now, because I have an accessible floor and a not accessible roof, I will have live load and roof live load. So I will have two load types this time. Okay, I will have only one case for the wind now. Or let us make it two cases because the bracing is single diagonal. So the axial load will differ. Wind load 1, stick it, copy, and wind load 2, it will be in the opposite direction. And then I will add the temperature cases. Now we will start applying the loads, and we will start with the dead load. Now, most of the times when we have a truss, we need to increase the factor more than 10 or 15% because most of the times we have gusset plates for the connections of the truss elements with the cords. So depending on our connection, we can assume this value. For this example, I will assume it to be 1.2. So 1.2 to 1.25 for truss, it can be a good assumption. And now I will add the floor load. But before I do that, let me do something. I will assign groups for the floor and for the roof. So here, selected objects. I will hide the angles and I will assign a group and it will be floor. And I will do the same for the roof. So I will call this roof. And here we go. Now I will apply the load on floors rather than to apply it as a member load. So I will not use member load. I will use the floor load and I will choose the group and I will choose the floor or the roof. So now let us start with the roof and let's go back to my loading criteria. On the roof, I have a total of zero point 0.7 kilonewton per meter square. So I will go here and choose minus zero point 0.7 because it will be in the minus y gravity direction and it will be one-way distribution. Now, if I choose one-way distribution, which means that the load will be applied only at members spanning in one direction. It will not be applied at all members. Okay? So now towards longer direction, which means that if I have this span, so the load will be applied this way. However, if this member and this member, they both have equal length, such as my case here, I can see that I have equal width with equal spans. So in this case, I will go and choose the distribution towards the needed member label. So I will say, for example, I'll need it to be towards 97. So I'll go and choose 97 and I will choose add. And here, as you can see, the load will be applied at the members which are parallel to the z direction. Let me now just the scale distributed load. I'll make it a little bit smaller here. Okay, now you can see the distribution of the load here. And I will do the same for the floor. So I will go before, let me check the total load on the floor. So it equals to 2.84 as we got it before here. So from here, I have a corrugated steel plate which equals to 0.76 mm. The RC slab 125 mm non-composite. Now I can calculate these values with the corrugation. However, if I know the supplier, I will simply go and for the required composite section, and I'm not using the composite action. However, the corrugated steel plate, I will choose 0.76 mm, and the self weight will be equal to 2.43 kilopascal for 125 total thickness of the slab, and this is what I already provided here. Okay, and for the screed, I have 20 mm screed finish. So 20 mm by the density of the screed, which is 21 kilonewton per meter cube, I got a unit or area load equal to 0.41. So the total load on the floor will be 2.84. So I will add floor load again, group now floor minus 2.84, one-way distribution. If I choose now longer direction, you can see that the load will be directly applied at the longer members. So because the grid here, you can see this will be 1.5 and this is 3. So no need to specify a member label in this case. So it will be applied uh, towards the longer members. Okay, and that's how I apply floor load. Also, I can apply it as a distributed member load. However, I need to calculate the tributary area in this case and apply the load on the members. So this is a quicker way in case I'm using or I have a grid system or a flooring system. So it will be much easier to use the floor load. Okay, now I also need to apply the load on the walls. Here I have a curtain wall with double glazing. And as I said before, we need to understand how the cladding is supported on my structure. Will it be supported on columns or on beams? Most of the glazing systems, the curtain walls, will be supported on beams. So the load will be supported maybe on top, on bottom, or shared between the two floors. So depending on the fixation of the glass, sometimes I have a vertical slot for the connection of the glazing or the mullions for the glazing with the steel, and sometimes it's hanged from the top level and only laterally supported from the bottom, or it can be supported both at top and bottom. Okay, so it depends on the fixation of the glazing on my structure. Now, for me, I will assume that the load will be supported on the bottom level and it will be vertically free at the top. And most of the time, it's preferable to support the glazing at one level only to this will be more helpful in the serviceability issues in case I have difference in the stiffness between the two levels. Sometimes this level will deflect more than the lower level. I'm not talking about this case, but in general. So if I'm only fixing the cladding at one level only, so I will ignore this impact or the differential displacement between the two floors for the serviceability checks for the glazing, for example. So now I will apply it on the lower level. It's 1 kilonewton per meter squared, and the height I have here is 3, so it will be 3 kilonewton per meter. So I will apply it as member load minus 3 in the y, and it will be applied on the lower chords. And now I'm done with the dead load application. So let us move to the live load. The live load will be applied at the lower level, and in this case I need to check the serviceability, or sorry, I need to check the occupancy of the floor this bridge is serving. So let me go back to the table here. Most of the time, this bridge will be a corridor between two rooms or two apartments or two areas. Okay, so it will be most of the time as a corridor. So if it's at first floor, the live load will be equal to 4.72, and in other floors it will follow the occupancy of the floors it serves. So if this bridge is spanning between offices and offices, so I will take the category as offices, and I will apply the live load for offices if it's above the first floor. However, if it's in the first floor, I will take 4.79 kilonewton per meter squared. Why is that? Because most of the time, the first floor or the first corridor in the building, in the first floor, I'm not talking about the ground. The ground for sure, it will be an assembly area or a lobby or reception. But in the first floor, it will be congested with people most of the time. Maybe people will gather there to go to other floors or to go to this floor. However, as you go up in the floors, the people in that floor or on that corridor will have something to do with that area. If they are working in that offices, or if they are working in like a kitchenery, okay, so the corridor for the kitchen will be mainly for the people who are intended to use this kitchen or visit it. This is the philosophy behind the values for the live load for the corridor. Now we will assume that it's in the first floor, so we'll add live load value equals to 4.79. For the roof, we will go and apply the 0.96, which is for ordinary flat roof. And I will check if I can have a reduction at the value. However, the tributary area will be 9 meter. So in this case, I cannot have any reduction for the roof live load. So I will apply it with the full load minus 0.96. So I will choose now towards any of these members 97, and here we go. Now the wind load, I will apply it one time in the positive Z and the other time in the negative Z. So I will have it 1.2 kilonewton per meter squared on the windward and one on the roof, and it will be applied on the cords when I apply it on the walls. Why? Because the cladding is supported on the walls. So I cannot apply it on the vertical members because the cladding is supported laterally at these two levels, and I assume that vertically or the weight will be supported at the lower level. So the height of the truss is 3 meter. So the total load, it will be 1.2 multiplied by 3 over 2 towards Z. 1.2 multiplied by 3 over 2, it will be 1.8 in the positive Z, and for the roof, I will go and choose the roof, and I will apply 1 kilonewton per meter squared Okay, now the wind in the other direction, minus 1.8 in the Z. I did not do any calculation here for this example, so I just assumed these values because we already had a detailed calculation for wind before for the previous example. So here I just assume these members to save time. Okay, now for the roof, 1. Okay, so the temperature load will be applied easily now. Temperature in the axial 20, and minus as well. And now I finalized the application of the loads. So let me now assign the direct analysis. Um, in this example, let us use medium grade steel. For sure, the flexural uh, stiffness reduction tau beta must also be checked as we said before. And I will apply the load combinations. Now I will apply the loads for all of the uh, members, okay? For all of the load cases, sorry. Because I don't have many lateral load cases, two winds and two temperature. So I will apply them now for all load cases. However, the checks, as we said before, can be applied, and in some cases I can apply the notional load at the gravity load combinations only. So now I finalized my uh, load application, and I will move to the analysis. I will choose analysis command, direct analysis, LRFD, and I will give the tolerances for tau and displacement. Now the tau beta here, I will uh, choose this checkbox. So tau beta will be iterated because I did not fix the notional load to 0.003. So I will add miscellaneous command. I need to set NL 500. It's okay. It must be more than the load combinations I have. Post analysis commands. I will choose all the load combinations I have. I will add and then I will run. Okay, let us see the output file. So I don't have errors or warning. I have 74 messages. It's like a note. And it's saying that PR over PY is exceeding zero point 0.2. Okay, because it's a truss. So I have high compression force in the top or top chord mainly, yes. So here I can see the values for PR over PY. So after checking here, I can see all the values for all the members. Here I have the highest value equals to around 0.75. So if I check all of these values, I can conclude that uh, around 0.75, 0.751 is the highest PR over PY value. So this value will affect tau beta calculation here, PR over PY. So simply, I can just check the value for tau beta, although it's iterative and STAAD Pro must calculate the accurate value based on PR over PY, and it's giving it to me as a note. However, I can check it also. So I will use this equation when I have PR over PY more than 0.5 and alpha equals to 1 in case of LRFD. So 0.751 PR over PY. So the result will be 4 multiplied by phi by this value 0.71, 0.751 minus 0.751. So here I can see that the value equal to 0.75. So what can I do now? Just for consistency, I will go back to the loading and adjust the value for tau beta to equal 0.75, and then I will run the analysis again. Here nothing will change. The notional load value will remain as is, and I will run the analysis again. Okay. Now let us go and see some results. For the gravity dead load, I can see the distribution of the forces at the top and the bottom chord. Here I can see that the top chord is under compression, the bottom chord is under tension. Here I have a zero force member, okay, because under equilibrium it will have no forces here. Okay, here I have a roller release, so it's a zero force member. So this is my model here. I can also check the moment value under wind load. So here I can see that mainly these portal frames are resisting the force or are providing stability for the truss in the z direction, because here the force will be transferred to these portal frames at the end, and then it will be transferred to the support through this portal frame. So I can expect a slight increase in the section for these profiles at the end here. All other checks I can check them after I finalize my my design. So let us now go to the design stage, and we will start to add the parameters. So I'll choose 36010. I will start with the method LRFD add beam, assign to view, CB value. I'll choose it equal to 0, so the software will calculate this value automatically. Now I will go to the assignment for F ultimate, and F ultimate approximately it will be around 420 megapascal or 410 megapascal, and the F yield it will be 275 megapascal, because I assumed medium grade steel as per the European standard. The American, we don't have this grade. However, if I'm using European profiles, which are IPE, so most probably I will have European grades for my steel. Okay, K value will be equal to 1 because I'm using direct analysis. So now let us check Ly and Lz. Now for the top and bottom chords, LZ will be the distance between the bracing or the vertical truss elements, because this chord is only braced vertically at these points. So LZ for top and bottom chord will both equal to 3. We see that LZ is the rotation around the Z axis, which is here the green axis. And always I need to look at the local axis when I'm assigning these parameters. So I will go and choose LZ equal to 3. Okay, now for LY. By the way, for the top chord, it's segmented at 3 meters. So the nodes are added each 3 meters. So if I did not add this parameter for the top chord, it's okay. Now for Ly, buckling around the minor axis, and it's very important to assign these parameters. Why? Because mainly the forces in the truss are axial and axial compression and tension. So the moment value is much less than these values for axial tension and compression. This can be seen easily. If I go here and check the graphs, and let us, for example, under dead load, let us check the moment value in comparison to the axial load. You can see here for the top chord, I have around 404 kilonewton axial in comparison to around only 5 kilonewton meter moment. So the governing force in the truss is the axial force. Also here, you can see that the diagonals will mainly be under tension for a Pratt truss. So that's why it's a preferable type of truss, because in this case, these diagonals will not be under buckling. Okay, let's go back to design. So as I said, LZ will equal to 3 meters, the distance between the vertical truss elements. Now for Ly, for the top chord, also it will be the distance between these crossing beams in the short direction, and also I do have horizontal brace, so it will buckle around these points or brace points. Now for the bottom chord, I have a segmentation here. I'm adding members each 1.5 meter. Also, as I having a concrete slab on a metal deck, most probably this slab will be fixed to the beams at around 30 centimeter to 60 centimeter, which is mainly the distance between the ribs. Okay, so here if I can look at this, the spacing between these ribs is around 30 centimeters. So if I'm fixing the uh, the corrugated plate with the steel beams top flange each rib here, so this spacing will be around 30 centimeter, and if I'm fixing it every other rib, it will be around 60 centimeter. even if I'm not using any composite action, even if I'm not adding any shear studs, only fixing it by screws or bolts. So in this case, Ly will be the distance between the fasteners. So it can be each 30 or 60 centimeter. However, conservatively, I can assume it the distance between these secondary beams. So if I choose it to be 1.5 meter, it will be fine. However, if I'm using a slab, a concrete slab on metal deck, I can use it as the distance between the fixation of the deck with the steel beams. Okay, so I will choose the distance between these ribs, and I will choose each other ribs conservatively. So it will be 0.61 meter, and this will be assigned at bottom chords. Now for the truss elements, I don't have any, let's say, segmentation or any physical node in these elements. So it will be as is. Ly and Lz will be the full length of these members. So I don't need to add any values. Now for the secondary or the beams in the short direction, here also Lz will be the length of the beam and Ly also will be the length of the beam. Now for the bottom chord, Lz will be the length of the beam and Ly also can be the distance between the fasteners which are fixing the metal deck to the beam top flange. So I will also now I can select beams parallel to Z. I'll choose the bottom chord and I will add the same value here. Because they will be fixed with the concrete slab at this distance, so it cannot buckle in separation alone. It cannot buckle alone. It will buckle if it will buckle with the concrete slab. And by the way, the in-plane buckling of beams, mainly in a composite slab, or even if I have a proper fixation of a concrete topping with my steel beams, it will be very improbable and it's not common at all. Okay, so now let us go to the remaining parameters here for the net area for tension members. Now for the top chords and the bottom chords, I can take the value as 0.85 for the trusses. You can use it as 0.85. And by the way, we can use it for all the members. In case I have openings, noting that the connections will be designed separately after I finalize my members, so I don't need to worry about the connections now. So if I take it 0.8 to 0.85, okay, on a conservative side, I'll take it as 0.8. So you can use this value always for the trusses. Then, if I need to increase the allowable slenderness ratio, I will not use this now. And now I will use UN top and UN bottom for LTB, lateral torsional buckling restraint. So now, for the chords, the UN top and the UN bottom will be the spacing between the secondary members here, because these members, if I look at the connection here in 3D, any type of connection, when I have a closed section depths, it can restrain the buckling of the compression flange and the rotation of the section. So any connection here will provide a suitable, for sure I need to check it. I need to check it against required stiffness and strength. However, most of the time, if I'm providing proper connection that can resist the applied load at this joist, will work properly to resist LTB, especially that I have a composite or a concrete slab at top of these members. So the concrete slab will ensure that the compression flange will not go anywhere for the main chords. Okay, so the unbraced length of top and bottom flange for the bottom chord will be the distance between these secondary beams. And for the top also, for sure I have these members as well, and also as well I do have these bracing. Okay, this bracing for sure will provide me bracing point for the chord against LTB. You can check it also. If you need to be more sure, you can go back to the equations for stiffness and strength of the brace point and ensure that these bracing are working with you properly. Now here, for the secondary members, they can be the full length, so I don't need to add any parameters for UN top and UN bottom. And here, if I am using the knee bracing, if I'm using knee bracing with the flanges, I can decrease the value for UN top and UN bottom. However, the length of this member is around 3 meters, so I don't need to provide these details for knee bracing. So I will keep the UN top and the UN bottom for the top, the beams at the top level as is. Actually, for bottom chord, the full floor, UN top can be taken as 0.61 as well. Why? Simply because, like if I have here a beam and I have this metal deck, and it will be fixed with these beams at this interval, and here I have a concrete topping, so for sure these bolts with the concrete will provide restraint for the top flange. So the top flange will be restrained by this concrete, which is acting as a rigid diaphragm, and it will not allow the flange to laterally buckle at the full length of the member. So also in this case for the bottom chord main beam and also the secondary beams, I can add U on top equals to 0.61. However, if I don't need to rely on, okay, sorry here. If I don't need to rely on the concrete slab, I can keep the U on top equals to the actual length here, which is the distance between the brace points for the chords and the full length of the secondary beams. Okay, so track, if I need to read the results, the calculation from the code, I can add this as well, and I can assign it to all of my members, and I'll add check code and takeoff. Takeoff for the quantities and check code for design. And I will run again. Okay, let us read the results. Okay, by looking at these results, we can see that the bottom chord unity check is around 0.855, so it's quite good. I can check a slightly smaller section, IPE 270, and for the top chord, I slightly need to increase the value here, so I can adjust it. So let me go back, and now I will choose two different profiles for top and bottom chords, and let me choose 270 for the bottom chord, and I will choose 330 for the top chord. Also, as you just saw, the portal frames here, due to the moment coming from the wind in the z direction, they are failing. So let me run again so you can check that with me. So in this case also I need to increase their profile slightly. I'm using tubular columns and I section for the beam. Okay, slightly failing, still slightly failing. Oh, by the way here, okay, now I reached 0.985 for the bottom chord, which is perfect as unity check. It's very economical. Now, as you can see here for the portal frames, because they have moment value, you can see here, I have around 47 kilonewton meter. However, at the other frames, the moment value is much less. Here it's coming from the gravity load, because this beam is spanning and it's carrying the load, gravity load, flexural load. These columns are barely carrying any moment value. They are released and purely axial members. This is common for the truss. You can barely see any moment value at the diagonals or the vertical members. Also, you can see here for the top and the bottom chord, I have around 793 kilonewton tension. For the bottom chord, it will be under tension, and the top, it will be under compression, around 900 kilonewton. However, I have less than 20 kilonewton, around 15.6 kilonewton meter moment. So the truss, it will transfer the moment values into tension and compression couple force. So let's go again here. I will choose 360. For sure, if I'm using built up sections, I can save more material. I can choose the thicknesses and the widths. And for these portal frames, I can, okay, I will choose the same profile here. And for the vertical, I can go up to I need to keep the width of the section approximately. Let me think about the connection also. If I need to make the column above the beam, so I can limit the width of the column approximately equal to 135 or less. Or if I want to make it extended, and then the beam will connect to it like this here, so I will not have a problem. Anyway, let me change the section now. I can go and choose a rectangular section, by the way. If I choose 180 by 100 by 10, okay, I will rotate it. So the major axis will act in the other direction here. So I need to rotate these columns. So because I need to resist the moment coming from the z direction. So I will provide them 90 degrees angle. Or for sure I can use a box section, square. So in this case, I don't need to rotate anything. Let me run again. Okay. Here I can see that now the profiles are all safe. The top chord is around 0.9. You need to check the bottom chord is around 0.98. So the top and the bottom chord are optimized. However, the diagonals, they can be optimized for sure. Here I have low stress value, so I can use lighter sections for sure. As I go to the edges of the truss, I can see that the unity check increase. So, but also here it's quite low, it's below zero point 0.5. So I can optimize the truss by reducing the profile of the vertical and the diagonal members. But I will leave that for you to do that. The optimization step is pretty simple. So all you need to do is to go and maybe decrease the thickness a little bit. You can start by decreasing the thickness because it will give you a good saving in the material rather than to start by reducing the depth of the profile. And after that, if you still have low unity check value, you can reduce a little bit the uh, outer dimensions. So you can use 100 or 80. So I will leave this step for you. Okay, now let us uh, go and check the serviceability. But first, let me add the serviceability load combinations that I need to check. I will add them through the command file. I'll go to the latest combination I have, and I will now list the serviceability load combinations. I will start with 80 after the latest number, the last number I have here. So this will be dead load plus live load. And let us get the serviceability load combinations for dead plus live when I have live and roof live. So it can be dead plus live, dead plus roof live, or I can have dead plus 0.75 plus zero point 0.7 roof live if they come together. So I will assume 0.75 of each and I will add them together with me. So the first one here, dead 1 will take a factor of 1 and live 2 will take a factor of 1. So the next one will be dead plus roof live load, which is here 3. So I'll just change the load case number. And now I'll take 0.75 roof live load plus 0.75 live load. Or conservatively, you can take them together with the full load. But I'm following the ASD combinations, so I must be fine when they come together. Okay, now I will have the wind load combinations. So for the dead, it will take 0.9 and the wind will take 0.45 because I will have the 10 years wind speed. So it will equal 0.750 years wind speed, which approximately equals to 0.45, the ultimate wind speed. Here I assume that I'm considering an ultimate wind speed, so I will take wind, which is here 4. The factor will be 0.45 and the same for the wind in the other direction. 2. Here also I need to adjust this number, and let's run. Okay, so I'll go to the summary and I will list the load combinations for serviceability. So the highest value for vertical displacement, it's around 65 mm. Because I'm using direct analysis, so I will multiply this value by 0.8 because I do have a reduction on the material stiffness. So I will consider 65.08 by 0.8. So I have a total of 44.86 mm as a vertical deflection. Now for a lateral deflection, I have around 24.334. This is vertical. And as a lateral, for sure, the governing will be in the z direction. It will equal to 24.589 by zero point 0.8. So it will be around 20 mm. Okay, so these are the values. And now I will check the displacement for the floor here. The displacement dead plus live must not exceed the span over 240. Let us go back to the code requirement here. For floor members, dead plus live must be less than L over 240. And for roof supporting non-plaster ceiling will be less than length over 180. So the governing will be the floor member because both cores will deflect together because they are part of truss. So here the span, which is the span of the truss, 30 meter over 240. So I have a limit of 125 mm. Laterally, it depends on the cladding. So here in my case, I have a brittle cladding, brittle finish. So under wind, it needs to be less than L over 240. And here I need to consider the displacement, relative displacement between the top and the bottom chord because the fixation of the cladding will be at top and bottom chords. So I need to take the drift value, which is the lateral displacement at top minus lateral displacement at bottom. So here I will go and select the critical combination, which is 0.9, and I will read the value here, 26.9. No, sorry, the Z 24.322 approximately here. Let's see the highest here, 24.334, 23.555, Okay, so let's take this, and the lowest chord Z will equal to 2.421. So here, if I need to get the final displacement here in the Z direction, so I will just deduct 24.334 minus 2.421. I will multiply them by 0.8 as well. And the limit, so here it's slightly exceeding. So there's a good way to increase the stiffness at the midspan in case I have a high displacement in the Z direction. Although it's not really high, however, I did not meet the limit here. So what to do? I'll go back here and add an additional moment frame at the center. So here I will remove the releases from this member here and also from the column joint with the beam, and I will use the same profiles I use for the end frame, and also I will rotate it you can see here. So I'll have a stiffer frame at the mid with a moment uh, with a moment connection. So let us run the analysis again and see the impact. You will notice a decrease now in the displacement value. So if I go again to the value under consideration, here I have 17.435 minus at the bottom it's 3.625. So it's 11 mm. So now I did meet the limit for the displacement in the or the drift in the Z direction. Okay, so now the global displacement for the bridge are okay. However, now if I have curtain wall panels that are supported at the bridge here, so I need to check the in-plane or the racking displacement of the panel itself. So let us now go back to the displacement slides. For this panel here, I need to check in-plane displacement, vertical drift, and in-plane racking value, which is delta R. Now delta H out of plane, uh, I already checked it. It's H over 240. So now in plane, delta R, I need to check the displacement relatively between the top and the bottom chord here. So let's go to the most critical panel, which will be at the edges, because here I have the minimum displacement and it will start to deflect here. For sure, I can check more than one panel. Let me now check this one. So here I will start to check it under for dead load prior to cladding, which means like here the self weight. So in this case, I need only to show the self weight of the structure without any applied load. You can do that. However, let us check now these values. This is the total dead load, and this is the dead load including the cladding weight. So this is mainly for the curtain wall, and this can be applied for the partition wall. So this is more critical actually. So now here L over 600. So let us check the limit here that I have. Select. So here I have 5 mm, and at the top let us get the local displacement at the mid. From dead load it's almost 0 here, and here due to dead load let's confirm the value again, it's 6 mm. So if I multiply 6 by 0.8, it's around 4 mm here at the middle. So I have a displacement of the panel equals to 0.4. So delta V must be less than the span, which is 3 meter over 600. Which is around 5 mm. So, which means that I am fine. So I did met the limit here because I have around, as we just saw, it's around 6 mm. If you multiply it by 0.8, you'll get around 4.8, 4.9 mm. So it's fine. And as we mentioned before, this limit is quite conservative because it's given in the code in case you don't have any data from the curtain wall supplier. However, the curtain wall supplier will give you most of the time more relaxed values depending on his fixation of the curtain wall on the structure. For sure, you can do and check the other panels. However, most of the time you will see that you will have the critical ones at the edges. Here you need to check the displacement, for example, for this panel in relative to these points because you need to check the local deflection of the panel itself. So for example here 31 and here 32.6 and here 28. So you have around the 3 mm displacement. So most of the time here you will be fine. And in case we are actually fixing the curtain wall panel on the bottom chord as we assumed, so you need to check the displacement of the bottom chord only, not in relation to the top chord, because I'm fixing it only at the bottom chord. However, if I'm fixing the panel at the top and the bottom chord, in this case I need to get the relative displacement between the top and the bottom because they will have an impact on the panel together. It's like this here. This is my case. I'm like providing a vertical support at the bottom chord. Assume that these are the chords, and at the top chord I have a slotted hole. So the displacement of the panel will be influenced by the displacement or the deflection of the bottom chord alone here. So here my truss is adequate strength-wise and serviceability-wise. You can then check it here. Serviceability, which means deflection. So the final thing I need to check now is the vibration of the truss, and I will check the frequency. I need the frequency, the vertical frequency, to be more than 3 Hertz and the horizontal to be more than 1.5 Hertz. So let us do that. I'll go to the loading and I will add load case. I'll call it vibration. And here I will go to the frequency model calculation add. I'll copy the dead load case. So first I will check the vibration, the vertical vibration. So let's go here. And don't forget, in the analysis, I need to add cutoff mode shapes command. Let us use 10. And also, because I don't need to have a reduction in the stiffness, I don't need to use the direct analysis. So I will use perform analysis. And now let's run. Here I only need to check the vibration. I'm not checking any unity checks or displacement values. That's why I changed the analysis type. Now let's go. Post-processing, dynamics, and let us see the first mode shape. If we need to know the value, it's 3.376, which is more than 3 Hertz, which is quite fine. And by the way, when you provide the slab, the concrete slab, when you model it here, assume you want to model the concrete slab, you'll go and model it as plates. Add the plate and you will choose the thickness and you will just model it. For example, let me show you quickly. You'll do it like this. And then you will go to the profile and choose the thickness for your concrete. For example, it will be 15 centimeters, and you will assign that to your structure. In this case, you will notice a significant increase in the vertical displacement. I'll not do that this time. You can check it on your own because here I have an additional stiffness for my model. Okay, now let us go and check the lateral displacement of the truss. So I will choose the Z direction, which is the critical direction here. I will change Y to Z, that's all. Again, we will run. and the frequency is more than 1.5, so it's fine. And these limits are provided to you here. Actually, the lateral, uh, as per design guide 11, it's okay to be more than 1.3 only. It needs to be more than 1.3 for floors. For the stairs, we have quite higher limits. So my uh, bridge is okay. Also, in terms of frequency, so I can say that my model now is adequate, strength-wise, serviceability, which means deflection and vibration. You can do more optimization for sure, and you can also model the concrete slab if you want. You don't need to add it in the self weight. You only can add the property, so the stiffness of the bridge will increase. In this case, when you check the vibration, you can see that there's a significant improve in the frequency value. It will increase for both vertical and also lateral modes. So that's it for our model, and we'll see you next time.